Good afternoon, everybody. My name is Chris Lubkeman. I am head of the Strategic Foresight Hub at ETH Zurich. The Strategic Foresight Hub is working in close collaboration with the AI Center at the ETH to bring a series of dialogues, spotlights, and labs on very specific topics which the AI Center is focusing on. These three specific topics of this trilogy of events of Spotlight, Lab, and Dialogue are quite interesting because they allow us to dig into the research of one individual researcher and then to dialogue around this domain, what this could mean, AI and this domain, and then the dialogue, which is a little deeper dive, longer dialogue with this researcher at ETH that we get to have the pleasure. Today, our guest, our dialogue is with Professor Daniela Domeisen. And
Good afternoon.
Hello, it's great to have you here. And you are a professor of atmospheric predictability.
That's right.
Now, I think we're going to spend a whole next hour talking specifically about atmospheric predictability. But before we do that, why in the world did you get into this domain of atmospheric predictability? And first of all, you might explain exactly what that is and then why.
Sure. So I guess that was a gradual process. I started out in physics and then got into climate as I did a master's at Columbia University, where I really looked at like applications of climate, like why, how does climate affect societal processes, especially in developing countries. Then I felt like, I need to know a bit more about this climate part of it so I can actually, give some kind of expert opinion on things. So I went to MIT to do a PhD there on climate physics.
Mm-hmm.
And after that, I got into predictability. So I first learned kind of about how the atmosphere works and things like that. And then I went to Germany, to Hamburg, to learn about and to build a model literally for the German weather service that we developed there, to understand how can we actually make long-term predictions. And then after that, I felt like, okay, now we need to actually apply this. And we need to actually understand how is this relevant to society. And I went into private industry to a commodity broker in London, where we used weather variables, but also economic variables to predict prices for commodities like coffee or iron ore or electricity, things like this. And then after that, I got a professorship in Germany, and I kind of started bringing things back together, the applications part, the theory part, and working on climate and predictability, trying to understand how the atmosphere and the whole climate system basically evolves over the next days, weeks, months, and so on.
Mm-hmm.
And then almost 4 years ago, I came to ETH to deepen that research and build a group here.
Well, it's fantastic that you're here, and seriously, I'm really glad. And that's just how. So you went in to understand. I get it. So you started in physics, and that's basically big math, and then you started to try to understand why and how the atmosphere moves. So how does the atmosphere move? Well, what are the drivers behind that?
Well, the main driver is the sun, because
Okay.
basically we get heating in some places, we don't get heating in other places, or we get less heating in other places. And therefore, since as everything in physics, you always try to kind of reach some equilibrium.
Mm-hmm.
So the Earth is constantly or the atmosphere is constantly trying to transport heat to equilibrate. However, the entire system then, in addition, is rotating, which makes things a lot more complicated. And there is a constant input of solar radiation that varies over the day, over the year, and so on. So basically, things are constantly moving, and we're trying to understand why and how this is happening.
Okay, so it's basically the energy for the system, if you will, and for has been coming from the sun, and then more recently from humans. We've been helping that energy, putting some of that And
We're
energy,
trying to keep as much of it as possible in the atmosphere, which is maybe not such a good idea.
yeah, that's not such a good idea. It gets a little bit excited up there, then I guess you could say. Yeah. So if we think about this big Earth and talking about your professorship in predictability, you're essentially trying to make a model to help you make these predictions. This is what you're really doing. You're modeling. So, what is a model? Give me an idea, because when I was a kid, I made models with plastic and glue that you'd end up sniffing and getting high and all that kind of stuff. But wood and plastic, you don't use wood and plastic, I don't think, and glue.
I use wood and plastic to make little trophies for when my students win a prize, but that's a prediction competition. But the models that we build in our research are slightly different. So what what we do basically is we have a range of different models, but
Mm-hmm.
the whole idea of having a weather prediction model is the kind of really nice aspect is that we have governing equations. So basically we have equations that was discovered just a bit more than 100 years ago that we can actually describe the things that are happening in the atmosphere using equations. And that wasn't so, I mean, it's not obvious, right? It's like, it's not something that that you would immediately see because a lot of other processes that are happening don't actually have equations. So that's a nice thing about the atmosphere. So we can use those equations to then, and then, we can put them on a numerical grid. We can integrate them forward in time because they're time dependent. And we can then, theoretically, you would think that you could basically just keep integrating forward in time and then understand what the weather looks like in 2 weeks and a month and so on. But then there's this whole chaos theory thing that tells us, well, it's actually not that simple. And that was discovered only like 60 years later after we had enough computing power to actually figure this out. So that makes the whole process a lot more complicated. But the basis is we have equations that we can use in order to model what's happening in the atmosphere. But then, of course, there's also processes that we don't have equations for, like, for example, things that we need to derive empirical equations. So, for example, things like we're looking at biological processes or other processes that don't have such equations, where we need to say, like, okay, if this happens, then this always happens. And if we increase this one, if we double this one, then this one increases 4 times. So we can kind of have relationships in the climate system. These are more empirical, and then we add those to the system, and then that gives us like a whole complex system with all kinds of different parameters and processes in it.
So that's quite intriguing. So what you're just saying now is when we're looking at this, part of it is clearly defined physical, like models of numerical methods. Part of it is observational, where you say, well, we kind of know that happens in that. We don't know exactly the causality, but we're kind of sure that if that happens, that's going to happen. So in many ways, it's sort of a mix of science and magic. You're a magician.
Well, try to be. It doesn't always work, but
Well,
we do try our best. Well, so I mean,
yeah,
the difficult thing is really bringing those things together.
yeah.
So kind of bringing kind of our physical understanding of things and then the statistical relationships and then kind of merging those together. This is basically where AI comes in, right? Like, how can we derive relationships from things that we observe in nature, but where we don't have equations that describe that particular process? And that's really where we can use AI.
And so the AI, the machine learning, the AI is actually looking at patterns which you might not have seen before. Or what else is it? What other kinds of things might the AI be doing?
We can use AI basically for lots of different aspects
Okay.
in weather prediction. So, I mean, on the one hand, there is the issue that we have lots of observations, especially now lots of satellite observations since like the 80s. But there's gaps in those. So we can use, for example, AI to fill these gaps in data.
To extrapolate.
To extrapolate, for example, yes.
Okay, cool.
And then the next step will be actually feeding these observations into the model so that the model can actually use those observations. Like, so the model knows, okay, this is where we started from and this is where we need to go. And we can basically give the model information of where we started from, basically our initial conditions. And so those will have to be observations, but they will have to be fed into the model somehow. So we can use AI to kind of help the model do this. Then we can pre and post process the data that goes into the model or that comes out of the data. And then we can correct the biases that come out of our model, because we might see something that the model always predicts, but we know actually in Zurich actually it's always a degree warmer than the model predicts, so we can kind of make a correction to account for that. But of course, if you have to do this for every point on the globe, that becomes a lot of data pretty quickly.
Yeah, absolutely. So as you just said, so every point on the globe, that's a lot of data. How in the world you can't do this with the slide rule?
No, that would make it very hard. I mean, people actually did.
Really?
When they first discovered that that there is governing equations for the atmosphere, then people were like, oh, okay, great. So we can just compute the weather. We can just compute a forecast. And there was one guy, Richardson, who did this during the First World War. He actually did a computation using these equations. And it took him several months to do a forecast for the next 6 hours. So obviously the forecast was no longer valid at the time when he was done. And also the forecast was wrong, which actually turned out in hindsight that he just didn't apply enough smoothing, but the calculations were right. So, and also he did it during the war while he was an ambulance driver. So I guess that kind of counts in his favor. But basically then he imagined that, like, oh, okay, if he just had enough what he called computers, and he meant humans who actually do these calculations, then we would have a better forecast that we could actually deliver in time. And nowadays, obviously, these computers are machines, but that's what we're basically doing nowadays.
And so, so when you're doing your different models, so you do a model for like a week, 2 weeks, 2 months, 2 years, 100 years. So you have different scales in which you and your team and your colleagues around the world are working on. Can you give us an idea of those different time frames and the model which is sort of required with those different time frames? Give us an idea of the difference between those.
Yeah, this is actually a very active problem that's being studied right now, because, well, the ideal would be we can use the same model to do prediction a day ahead versus, climate timescales of 100 years. And we call this seamless prediction. So basically everything would fit together. We're not quite there yet. So we often have models that are good at, timescales of days to weeks. And then we have models that are good at timescales of, longer timescales, like months to decades or centuries. But the whole idea is to basically merge these, make them the same. And I think we're kind of at the point where we have the first models that can actually do this. But I think this is kind of a transition period right now.
Okay, before we dig into it, I just want to let all those who are listening to us right now live, you are welcome to suggest questions or ask questions in either in the Q&A button or icon at the bottom, which we all have known to love, and I will weave those into our conversation. So please do ask some questions, and I'll get them in there. So let's think about these models again. All of us are so happy and are so frustrated simultaneously with the way in which the weather is able to be predicted today. Happy because most of the time it's pretty right, and frustrated because sometimes it's not. Right? So why is this? Is it just like your professorship's about the predictability? Why can't we do 100%?
Well, part of it is due to this chaos theory part. So if you use just slight differences in initial conditions, and we know our initial conditions are never perfect because our observations are not perfect, and the way we assimilate them into the model are not perfect. So if you have slight differences, then we may end up, depending on different processes in the atmosphere, we may end up with a completely different state 12 hours later or a week later or so on. And this is a huge issue that was discovered in the 1960s, but that we're not going to overcome. But we have a better handle on kind of understanding which processes are easier to predict and which processes are more difficult to predict. So, for example, if you think about all the thunderstorms we're having in Switzerland, if Meteoswiss tells you on Monday there's going to be a thunderstorm at 2 p.m., you might not want to believe that exact timing of the forecast, but you might want to believe the forecast that it's kind of thunderstorm weather that afternoon. Right. But if Meteoswiss tells you there's probably going to be a really hot week next week, that's probably a more accurate forecast. So it always depends on what we're forecasting, exactly how kind of trustworthy that is. Interesting. That's not always communicated in exactly that way, because we always basically look at the forecast and we're like, oh, okay, that's what they're forecasting. So,
oh, I believe the forecast. I'm a fool, like, oh, darn it, I got fooled again, It's like,
well, what are you going to do, right?
Right. Yeah, that's true. No, but it's really quite phenomenal. You think how far we've come over the past decade, 20 years, and getting more and more granularity, which is quite striking. So I'd just like to focus on for a minute the difference between, say, weather forecasting or weather modeling and climate forecasting, climate modeling. What do we really need to understand about this fundamental difference between these two?
Well, actually, interestingly, that the fundamentals are actually the same. It's
cool. Okay.
Same principle. It's the it's the fundamental equations, same fundamental equations that we're using for both weather prediction models and climate models. It's just that some models are in their parameterizations, or think the way we represent processes are optimized for longer time scales or for shorter time scales. This is exactly the thing that we want to get rid of, in terms of we just want to have models that do everything right. But of course, that's difficult. But fundamentally, there's no difference between the two types of models.
Okay, so there's no difference between the two types of models. And how when we look at climate, we're trying to look out, say, 100 years. And how long does it take? I mean, how confident are you with some of the predictions, and how long does it take to put one of these models together and run?
That really depends on the complexity of the model. So I use anything from like super simple model to highly complex model that have lots of different processes. So basically the nice thing is we can basically go from, very simple models that have just very few processes to something that contains everything that we think we know. And climate models are usually the ones that contain all the processes that we, try to include. So that includes obviously greenhouse gases, the sun, the circulation of the atmosphere, the vegetation, the ocean, the ice, the snow, and so on. And obviously, the more complex those models are, the longer they take to run. So basically, we're always kind of at the edge of needing more computer power for weather and climate modeling. So all of these highly complex models have to be run on supercomputers. You can, depending on the simulation, if I have a very simple model, I can run it on my laptop and it takes like 10 minutes. If I have a very complex model, it can take me weeks to months to get a full simulation of what I'm actually trying to show. So yeah, it really depends on the complexity.
So, okay, so we've seen in the news recently quite a bit about the digital twin of the Earth. And that's a fairly complex, I'm imagining that's a fairly complex proposition, right? In order to get, is it sort of garbage in, garbage out type of thing? So what's the granularity which you would suggest in the complexity that we need to get to in order to have something which is meaningful and useful?
Well, the whole kind of digital twin is, depending on who you ask, you get a different answer what a digital twin is in the first place. But there's this one initiative from the EU where there's called Destination Earth, where they're basically encouraging people to build these digital twins. So the European Center for Medium Range Weather Forecasting, for example, they are building a digital twin that's includes basically all the data that we have currently, the best models that we have at the highest granularity that we can have, and tries to also make these data accessible to people, including AI methods, the actual model itself. So the interesting thing then is that this also then starts involving the public, right? Because people can actually use that data in order to, do analysis, check things that are going on. And it's not just the weather, it's also impacts that are going on based on these things, which I think will be really important for impact modelers, because basically right now they're getting data from weather models to put them into the impact models and then get an outcome. But I think maybe this can also be streamlined into building it all into one model.
So
and this is partially already done.
So granularity. So what are we down to, like one? If we take the Mother Earth, which is behind you, are we down to like 1 kilometer squares, or half kilometer, 200 meters, or is that the wrong question?
That's an absolutely great question. If we use global simulations, if you really want to simulate the entire Earth, and we want to do a climate model simulation, basically going out 100, 200 years, we're not at that level yet. So we're more, right now we're trying to get towards like 5 or 2 or 1 kilometers for really global simulations. What is often done right now is that global simulations are provided at slightly coarser resolution, and then there is nests of like smaller models within that that have much higher granularity, where you can do very detailed simulations. And then within that, you can then use like impact models that actually look at, will this street be flooded, or actually going down to the street level. But we currently have no chance of doing this on a global scale. That would need a lot more computing power.
We could just maybe somehow take all the Bitcoin miners and dedicate those to climate modeling. We could sort it out in about 2 days, probably. It's like.
Sure, I'll take mine up.
Yeah, I'm just kidding. So when we look at this, we've been talking about AI. Are there specific AI ML models for climate, or are we sitting here talking about sort of, I'll call it quote generic or non-specific methodologies?
Well, a lot of the basically classic machine learning methods work very well for climate, and some of them have been used pretty regularly in climate science. But I think now, as fields are really growing together, and as also a lot of computer scientists are becoming interested in the weather prediction problem, and we are becoming interested in using more advanced AI methods, there's a lot more kind of intersection. So we can, a lot of the kind of basic classification methods or clustering methods, those are very useful for climate, because we're trying to understand, when is there an extreme event? How do we classify an extreme event? Is this weather pattern really different from this weather pattern for clustering methods? And then also lots of methods that are more dynamical, or from dynamical systems analysis. So a lot of these methods can basically be directly applied to a lot of the climate problems.
Okay, so because I know some of your work, you just mentioned extreme, which triggered in my mind. I know quite a bit of your work, or some of your work and your team, is focusing on trying to understand and model extreme events. And what do you mean by an extreme event?
Well, one of the definitions of extreme is it has to be very different from what's normally happen, and it has to be relatively rare. So it doesn't happen all the time, because otherwise it wouldn't be very different from what's normally happening, right? So this can be heat waves, for example. It can be rainfall extremes, can be cold spells, can be extreme wind events, any of these types of events. The interesting part of those is that actually some of them are more predictable than regular climate. So we showed, for example, that heat waves are more predictable than just regular weather. And the other interesting part is that we actually want to predict these events, right? Because if we just say, okay, the weather is going to be normal for the next 3 weeks, that's a nice prediction, but it's not really. We don't have to issue any warnings. We don't have to basically people don't have to know about this as much as if there's an extreme event coming where people would actually have to prepare, municipalities might have to provide some services and so on. So that's what makes them really interesting,
So,
apart from kind of the physical parts.
so how far out at the moment do you feel you can begin to predict some of these extreme events?
So that again depends a lot on the extreme events. So for heat waves, we're currently often at about 2 to 4 weeks already.
Okay.
Cold spells is less. That's more like 2 weeks. For wind and precipitation, that's much more difficult, except sometimes when there is other regions of the globe that impact that particular region where the extreme is happening, then we can actually make better predictions of them.
Mm-hmm. So, that's interesting. I mean, 4 weeks that can really allow a city, let's say, like, I don't know, 5 years ago, Paris had a heat wave, and so many people, so especially elders, died. Because the city just wasn't ready. So this is a good way to help urban or farmers being able to know when they need to deal with their animals or something like that. So 4 weeks
Absolutely,
should 4 weeks should be enough time to help us. So that's really so. Is your goal to try to get that like 5 weeks, 6 weeks, 7 weeks, or is your goal to try to get more accuracy, or is it in the sense of is there both? Okay.
basically.
Yeah, of course.
I mean, we're trying to, yes. I mean, the ideal is to make the best prediction we can for,
Sure.
as accurate as possible. But yeah, I mean, of course, we want to go further out, but then, of course, the further out we go, the less accurate it's going to be in terms of, where exactly is it going to be? How long will it be there? How strong will it be? So that then becomes a lot more difficult. But at least, once we're on these time scales, we often have basically probability forecasts. We can just say like, okay, 3 weeks from now, we have a higher probability for this, but we can often not say the exact, how severe is it actually going to be? That's a much more difficult forecast.
Yeah. So one thing that's intriguing to me, and so I love the clouds. I love sitting there looking at them and trying to imagine the animals and everything I see, the flowers, etc. And the forces at work are quite striking. Really, and it's interesting how you said, which I didn't know that there are these governing equations, and you can make observations. But with AI, so much of it is a mystery how it works. And how do you? I mean, how do you feel about that? This is sort of a two-sided question. You've got governing equations, you have observing, and then you've got these black box things.
Yeah.
And as a scientist, how do you feel about that? Are you good with it
Yeah.
because it's a cool tool?
Well, yeah, it's kind of a two-sided sword, right? I mean, on the one hand, it's nice because you can process large amounts of data and kind of figure out relationships within the climate system. But then again, we have equations that actually already describe some of these relationships. So, I mean, there's a lot of effort in data science to make kind of physics-based or kind of AI that actually learns from physical equations. So part of it has to be this, and then the other part has to be kind of understandable. Can we actually follow what the AI is telling us? So so that it's not just a black box that we employ and we don't really know what's happening in between, but that we can actually follow why did it make this decision?
Yeah.
Because in the end, for us, like from a research perspective, we're not. I mean, we're happy if there's better forecast. But I'm even more happy if I can tell why the forecast was good. If it makes me understand something about the climate system that I can then use to make a better prediction. And so that's why these kind of non-black box AI methods are much more interesting.
Okay, so and you mentioned before how you very often would use, because I asked how are you using it, and you said, well, you're using it to somehow also fill in the blanks. But do you also use it to, like, I hate to say this, like to check the equations or to check the empirical observations, like just let the AI loose on what you already know to see if it.
I think this is not something we do in my group, but if there's parameterizations in climate systems, those are often checked using AI. So often, you know, relationships in the climate system are often derived just based on, you know, observed relationships. But then as you have AI methods, you can of course use a lot more of that data and derive these relationships empirically or statistically, and that often gives you a better representation.
Mm-hmm.
So this is certainly something that's done and can be used there for parameterizations in particular.
So, if you had a wish of all those who are listening right now who are deeply into AI, you'd say, hey, girls and boys, what I really need, what I really wish from your community is blank. Do you have an AI wish?
Well, I think it's mostly, I mean, it will not just be basically them giving something to me. I think it will be a collaboration.
Perfect.
So ideally, I think we have to combine the methods that we have, because on the one hand, we have fundamental equations. On the one hand, we have lots of data and we have AI methods. So combining those two, I think that's going to be what's going to happen in the future, because I don't think at this point, I mean, yes, we can keep making slightly better forecasts by making slightly better parameterization, using slightly higher resolution, slightly better process representation. But I think the biggest progress will be by combining these
That's great.
methods.
I like that answer. I'm a huge fan of the transdisciplinary interaction and all the challenges it takes. Like, because when you started getting into this, you had to learn a new language or languages.
It's a lot of communication, but it's nice because I think some of them are listening to the Swiss Data Science Center for People, for example. This has been a great kind of learning experience about learning about each other's sciences and trying to understand, for us, trying to understand what is really possible using AI, and for them to understand what do you have already, like where do we start from, and what do you really need. So yeah, it's a fun journey, and we're far from done.
Oh, that's really great. And so when you look at this right now, and we take a look at the computational power which we have at our fingertips today versus when you were in grad school, it's moved ahead by magnitudes. Has the predictability also moved ahead by magnitudes?
Yes, I mean, predictability kind of moves actually in a very similar way as computing power, because we're highly dependent on computing power. So, right now we can make a 5-day forecast where, 20, 30 years ago, actually that was before I went to grad school, but still,
Hey,
back then we could do like a 3-day forecast, right?
yeah, yeah.
So there's been a lot of progress there. So the question for me is mostly now, can we actually, instead of a more gradual increase, the weather prediction people call this like the quiet revolution of weather prediction. Basically, it's just been getting better and nobody's really noticed. But the question is, like, can we actually do any leaps, right? Can we actually really get a lot better at once? And
Yeah.
this is hard because there's so many parameters that are
Yeah.
kind of going
Sure.
into
No, I
this.
hear you. So let's come back to climate change for a little bit, because when you're looking forward with the predictability, can you tell me, are there a few things which your work with combining with AI has revealed which you didn't know before? Or are you still at the beginnings of this sort of collaboration?
I mean, some things that I find really interesting is that we've we always felt like, oh, we have the governing equations, we have these big models, so basically it can't get any better. We'll just have to like tweak little things and we'll get like a little better. But then sometimes we do find processes or combinations with AI that do give us a leap in predictability. So one thing, for example, we've looked at is connections between different parts of the globe. So for example, the tropics often have better predictability on timescales of several weeks than like Europe. Europe's actually one of the worst places on the globe to make predictions on weeks, 2 months. That's why studying Europe is so interesting, actually. But if we understand how other regions that have higher predictability influence Europe, for example, then we can possibly make better predictions.
Oh, that's
And
interesting.
so the fun thing there was that basically we looked at a super simple linear regression model, combined that with the numerical kind of the governing equations and the numerical model, and we got a huge leap in predictability. The problem there is still that we need to first use our physical understanding to be able to know what to put in our regression model, right? So I think there's a lot of space to develop there, for the AI model to find these connections itself, to figure out which ones to take, when to take them, which variables to take. So I think there's a lot of potential there. If already using a very simple tool, we can already improve forecasts by that much.
That's really cool. So, and if we're thinking about that again, coming back to climate change, we're looking forward over the next, say, 30 years, out to 2050. How confident are you with some of the predictions which we're seeing? And you mentioned it before, the fudge factor, right? Which is, people get Nobel Prizes for discovering a fudge factor, right? But, what are some of the fudge factors that we need to be thinking about that could be negative or positive when we're thinking about the predictability of the climate?
Well, I think, overall the predictions, all the models, even though developed from different sources, show us the same kind of trend. So basically we know where the climate is going.
Yeah.
So, the direction is clear. The magnitude is more difficult. And also the exact regional differences are difficult. So this is one of the challenges we still have, is it going to be this exact amount warmer in Zurich by this year? Probably harder than saying the Mediterranean will be hotter and drier, which is, I would say, basically certain, unless something crazy happens that we really haven't considered. And I think by now we've considered a lot of factors. And yes, but I mean, the hardest part about, looking at climate change is really the dynamics of the atmosphere. We know basically, we understand the thermodynamics, like we understand, sunlight comes in, we understand kind of more or less the water cycle, although we don't quite understand all the clouds. But then understanding how the atmosphere moves in response to different things, especially if you have different processes that go in opposite directions, that's one of the hardest things to still
interesting.
to still predict. And again, Europe is kind of in the middle of things, so that makes it pretty difficult. But in general, it's just going to get warmer, I guess.
Yeah. So, but does that ever just kind of bum you out? I mean, when you look at these, you are essentially, for our next generations, you can kind of see the predictability of what's, say, a most likely case. I mean,
yeah, it's a bit frustrating, I have to say. Sometimes I remember when I first kind of learned about the whole climate change problem, it was very depressing. I mean, I felt like, well, we have to do something about this, right? I mean, and I feel like that's how a lot of people, especially young people, feel like right now. And I guess after a while, you get a bit of a professional detachment from things. But, every once in a while, you still get back to that kind of thing. And you're like, oh, wow, we have to do something, right? And I mean, we do. But it's a bit different. Like when you're just working on your laptop every day, finding out different relationships in climate, and then thinking about, oh my God, this is actually going to happen to us. Then, it's kind of two different parts of my brain, basically.
No, I hear what you're saying. I think it's a big challenge. We're sort of observing the boiling of the frog, and we're measuring it. We're taking pictures of it. We're documenting
Lots of documentation.
We're doing incredible.
Absolutely.
Yeah. So if we take a look forward, there's a few questions have come in that I'm just going to pop at you, because I think I want to respect our listeners who have added these, because some of them are quite good. It says, and I don't exactly know how to weave them into a conversation here. Regarding bias correction of weather forecasts in the post-processing, do complexer or simpler machine learning models achieve a better skill? So this is when looking at post, how would you answer that? It's a
Yeah, that's actually, honestly, it really depends on the model that you're using. So sometimes you can get a very, already pretty good success with simple linear tools. And sometimes you have to go to like more nonlinear methods. But I don't think I can give a general answer that it's always the more complex tools or always the more simple tools. It depends so much on the application that you're looking at that, I mean, I'm usually a proponent of pick the simplest model possible and see what happens.
Yeah.
And if you can really show that the complex nonlinear method then gives you a much better result, then sure, yeah, let's use it. But usually, I mean, I guess as humans, we think in many very linear terms. So often it's much easier for us to understand what's going on there. But of course, if there's more complex methods that help, then yes. But yeah, there's no like blanket answer for this one.
It depends. It's a very valid answer. That's good.
Unfortunately, yes.
Yeah, I know. That's good. So another one's come in and says, how expensive is the computation power involved with atmospheric predictions? And I'm going to take that expensive, not just in cost terms, but actually processing power. Like, how much does it take? You said laptop versus supercomputer. Give us a little bit about that.
Yeah, that's a very good question. And honestly, I don't really have good numbers available in my head. But basically, if you can imagine you're running an entire supercomputer for weeks or months at a time, and yes, I mean, you can imagine that takes tons of electricity, tons of computer power, tons of cooling of those computers. So yeah, I mean, sometimes we think about, every once in a while somebody comes in and says like, maybe we should be more careful in like, maybe we're actually, accelerating climate change by computing what the climate is going to be like. But then again, there's probably a lot of other processes that use a lot more energy than we do.
Oh yeah,
so sure. I don't think we're the main culprit.
I'm happy to give you some of my electricity so you can do your work. That would be,
That's good to know.
Yeah, another question came in which I think is quite intriguing is around the question of how do you take into account potential when you're looking forward with the models, the potential of the positive human intervention? Because we talk a lot about the negative, but what about,
this is actually taken into account in the climate scenarios that we're using. So in the current version of the climate projections that we're doing, there's different scenarios, and there's basically only one scenario that says we're not going to do anything, like business as usual. And then all the others take into account some kind of intervention. So this goes from, geoengineering to sucking CO2 out of the air, to basically just reducing emissions or even basically stopping emissions. So yes, all of the scenarios that we use as input to those climate models include some of these measures. So yeah, unfortunately, the things that we see when we see the kind of the projections for where the temperatures are going to go, most of these actually already include human intervention to reduce climate change.
I'm assuming then it's also the ramping up more coal-fired power plants. Because you look at the tails of those graphs, it wags way up and way down. So
yes. So there's a lot of uncertainty. Cool. I always say, like, if you can tell me how the world economy is going to develop over the next 100 years, I'm going to give you a way more exact climate prediction of what's going to happen. I mean, honestly, humans are the major uncertainty in our climate.
Yep. Yes. And not just in Europe with the difficulty in modeling, right? That's just,
yes.
That's interesting. So another question is just right here is, what do you think, and what do you think are the most efficient ways that we could be reducing greenhouse gas emissions, top down or bottom up, when we're looking at, say, from your predictability? If you have any view on that.
Okay, I'm getting way out of my expertise here.
Okay.
So,
but you can punt. Yeah.
Basically, yeah, I don't know if there's like a best top down or bottom up way, but basically we just need to reduce them somehow.
Right. But
And whatever method works is
but do
fine with
you?
me.
Yeah, I agree with you that one. So, but do you think is modeling possible? Can you model the effects of, say, regulation or flight reduction? These are all possible to incorporate
Oh,
into your
absolutely.
models.
Yes.
Yeah.
I mean, people are doing this. I mean, this is already part of climate modeling. People use different types of regulation. People model how different types of reduction will impact both the climate but also human behavior and so on. So yes, there's tons of research on that as well.
Okay. And so the next one, the next question. Where do you anticipate the future of AI in climate predictions? Where do you anticipate, and what directions are in focus right now if you're in your collaborations?
So we still use a lot of kind of basic AI methods in order to basically get a better understanding. I think in the future, it'll be a lot more kind of interpretable AI. It will be a lot more kind of AI that we can actually kind of look into, interpret every step, kind of understandable AI that works kind of in tandem with weather prediction, because we know, I mean, we know by now that we can make some big steps by including this. So I think we'll go a lot more towards using more complex AI methods that
Mm-hmm.
will hopefully be able to kind of also use not just for basically better parameterizations or better gap filling or so on, but also really better understanding of the climate system. That's what I'm hoping for.
So, do you have a favorite place or on the planet that you like to model and study?
Basically any place that's very unpredictable. I just love those places where it's really difficult. And often these are places that have lots of different influences. So for example, I mean, Europe is one of these places.
Mm-hmm.
There is one of these places in Brazil, for example, that we've looked at. There's some of these places in Africa. It turns out, obviously, Europe is a lot better studied than some places in South America or Africa. So I basically like kind of trying to understand these places that people haven't really looked at or had the resources to look at, because researchers in the US, they study the weather over the US, and people in Europe, they study weather over Europe. But there's a lot of developing countries, for example, where weather and climate has been less studied, but there is lots of impacts in those places. And some of these are very unpredictable. So those are the kind of fascinating ones that I really like.
And so,
So
what about?
sometimes go ahead. So sometimes, for example, we use, for example, what happens in the tropical Pacific when you have El Nino Southern Oscillation going on there, that can have an influence on different places on the globe.
Mm-hmm.
But if that then interferes with other influences from, let's say, sea ice or the land surface, then the models quickly have trouble kind of simulating the kind of interaction of these effects.
Mm-hmm.
And that's the hardest part. And understanding the interaction of these effects, that's kind of the most fascinating part,
So,
in my opinion.
So the data you're gathering, you say, is it mostly satellite data, or? I mean, and give us an idea of the megabytes of data that you start dealing with. Yeah.
Well, yeah, I mean, honestly, I don't collect data myself. This is another huge effort that's going on, because basically, on the one hand, there's basically just pure data collection, and then there's also putting that data into a gridded data set, or the data set that's covering enough time so that we can actually study long-term effects. That's a huge science by itself again. So that's the interesting part. But a lot of it, yes, nowadays is satellite observations. So we can, that's the nice part, because then we can really observe large areas. We can look at lots of different variables. But then there's, of course, also lots of local measurements of things that we might not know. Like, for example, I remember in when I worked in the commodity industry, we always, we tried to model, for example, what's the weather going to be like for the next 2 weeks in West Africa. And it was really difficult to find out, for example, what is the soil moisture in a particular place in South Africa or in West Africa. That was just really hard. And there might be local observations, right? But it's difficult to access all the data, but some things are just not measured. So that was always kind of a difficult thing. So we actually had more predictions for how it was going to be then, but often we could not verify if these predictions had actually, if those were actually correct or not.
Yeah.
And that's still one of the issues. So more observations is always better.
And so how open is this global community with exchanging data? Is it?
It's a difficult topic. Some data is shared completely freely, and some data is difficult to access, and some data has to be bought. So it also depends, if you're in a research context, obviously it's always easier to access data than if you're in a private industry context. But yeah, and it depends on the variable that you're looking at. So, once somebody goes in and says like, oh, I want to create a global data set of something, then that's obviously great because you don't have to go to every country and collect this information. Yeah. But that's a huge effort to do this.
Mm-hmm. Yeah. It's a seamless exchange is always a bit of a challenge. That is true. But we worked it out with COVID. So, maybe, So if we think about... I want to ask you a different... we've just got a few more minutes left. I wanted you to think... When you think of 2040, are you an optimist or a pessimist?
Well, I'm very optimistic that we'll have better predictions. I'm very optimistic that we'll make a lot of progress in terms of understanding connections in the climate system, having better models, having combined numerical and AI models. I'm not very optimistic in terms of climate change, to be honest, because we're going to have heat waves like crazy. We're going to have refugees from places that are much more strongly affected in Switzerland. We're going to have, changes in how our electricity has to be produced. There's going to be so many changes that we have to deal with in a much shorter time scale than what people had to do in the past. We also have a lot more technology to do it, but the question is it going to be enough, right? Are we going to be fast enough to actually adapt to this? And I think a lot of countries will not be fast enough. That's what really scares me.
That's a very good prescient with very high predictability.
Yes, unfortunately.
Unfortunately, I think this is part of our reality. So, what should I have asked you that I didn't ask you?
Well, one thing I find interesting, for example, is using AI for climate change, because we're basically going into uncharted territory here. We're going to have a climate that we've never seen before, or if something similar was there in the past, we weren't there to actually take measurements and observe it. And we only have very limited observations for these times. And so, this is difficult for physical models in the first place, but for AI models, we need something to train our models with. We need some testing data, we need some training data. And so I think this is what makes me a bit nervous about kind of looking into the future, because we already have trouble, or I wouldn't say trouble, but it's already difficult to use kind of physical numerical models that have common equations looking into the future. But then if you want to combine this with AI, I think this is a huge challenge, because we don't really know what we should train our models with in order to look into the future. And this will be interesting. And maybe we'll develop some techniques that can do this better, but based on own relationships.
I think this is part of what the AI Center, what you and the AI Center are going to be working on, is trying to figure some of these things out. And that's really great to go into it knowing this is a challenge. We need to figure out to be able to use these new tools to help us understand what could be. Right? The context into which we were walking. So when I was a little bit younger, with Fortran 77, if you forgot a comma, you could let a program run for all night and come back and you found out you had complete junk. How is it with variable inaccuracy detection with your data? Like if some data is missing, do the models just freak out like they did 40 years ago, or do they?
They still freak out. Yes.
Darn! I was hoping you'd say, "Oh, they're so clever. They just, Okay.
I mean, yes. I mean, of course, if you have a lot more processes, so many things can go wrong in a model.
Yeah.
So yes, they do crash just like your computer does. So then we just need to figure out what to change so they don't. So yeah, they still do that.
Okay. Darn. I was. It's like the calorie and fat-free ice cream, right? That's still natural. Right. That doesn't quite exist. So if you were going to suggest to all those who are watching this and will watch this, 1, 2, or 3 articles, websites, pieces of literature of any kind to read to understand more about what you're doing and about, your research or seminal works on climate predictability, what would you suggest to our listeners?
I mean, I think some of the very nice articles and talks on Destination Earth might be interesting. So all the kind of information that's out there right now about digital twins and how this will be, also accessible to the public in the future. I think those are very interesting ones.
That's Destination Earth.
Yes, it's called Destination Earth, and basically underneath that topic there will be digital twins. Perfect. So that's basically combining high precision or system modeling plus AI and high resolution and impact data and so on. So basically anything you can find on this will be very interesting, because this will be an area where a lot of things will develop over the next 10 years or so. And this will also be an opportunity for people to interact with those models, to get data directly from there. So this is a nice thing. If you haven't gotten enough of my research yet, you're always welcome to. I have some of the talks on my website that I've given in the past on how you can connect different parts of the climate or on Earth, and how these things connect together. So that's if you're interested in that.
Well, those are two really great. So Destination Earth and your website. It's always not everybody has their talks on their website, or a place. So that's really great. So thank you for that. That's really wonderful.
I have to say, some of them are in German, some of them are in English, so you can pick.
Oh, there you go. English. Okay. So I'd like to thank you, Daniela, for sharing your passion, your drive, your hopes, and a couple of fears there with us on this day. And I want to thank all of you who've joined us for this now and who will watch this later. This collaboration between the AI Center at the ETH in Zurich and the Strategic Hub of the ETH in Zurich. And
thanks a lot. That was really a real pleasure.
It's really wonderful, and I wish you all the success. All of us wish you all the success with increasing your predictability, and for all of our benefits. So thank you so much.
Thank you very much, and thanks everybody for listening. And